This is our last lesson in exponents and logs, and we're looking at some graphs, and graphs that maybe our calculator can't do as easily unless we use the change the log feature of our calculator. Remember how to change the log. That rule is on your formula sheet. So I'm going to get a sketch of 4 graphs up here. Y equals log base 10x, y equals log base a third x, y equals log base a tenth x, and then a few more near the bottom. So I've got those graphs built. The log base 3, log base 10 are on the top and show some growth potential, but leveling out. The log base a third and log base a tenth are down below the x-axis. And the cool thing is, excuse me, the relationship between when y is 1, what is x? And you should note that the base value is that recording. I've been starting to fill in the charts, and you should recognize some of those features for log graphs. So there's 2 more graphs that you're asked to build, y equals log base 5x and y equals log base of fifth x. They should squeeze in between the graphs that we've already built. So the y equals log base 5x graph squeezes in between the log base 3 and log base 10, and the y equals log 1/5 also squeezes in there. Let's turn the page over. When we look at the relationship between the 2 graphs, log base 3 and log base a third, or log base 10 and log base a tenth, we see that what we have is a reflection in the x-axis. And remember, when reflections in the x-axis happened before, we were making y become negative y. That's the habit that's coming out here, and we'll try that out in letter G. The graph of y equals log base of 1 over bx is the what of the graph? Yes, we get that word reflection. Reflection in the x-axis. And now we'll just show how that happens using our log exponent rules. Just working with our log rules, I took the original statement and changed it into exponential format, switched the y to negative y, solved for a positive exponent, and then made a log statement, which allows me to have a nice equivalency. Log base 1 over b of x is equal to y, or y equals minus log base b of x. They are equivalent. So again, playing around with my ability to convert to exponential form. If log base 4 of x is equal to 8, that means 4 to the exponent 8 equals x. How can I evaluate log base 1/4 of x? Convert to exponential form. That's what I did in the first line here. And then I made my exponent change sign, or move the base up. And then I have what x is actually equal to in terms of base 4. So I have an x statement right here that says what x is equal to. And I've got an x statement over here. So those 2 statements must be equal to each other, which I've set equal to each other, and solve for y. Now take a look at what happens to a series of graphs where we've got log base 2, log base 4, log base 8. What seems to be happening to those graphs? We seem to be having a vertical stretch. Take a look at what happens to particular moments in time. So when y equals log base 2 of x, we find that when x equals 8, my y value is 3, because 2 to the exponent 3 is equal to 8. We'll try writing there again. 2 to the exponent 3 is equal to 8. If I go log base 4, 4 to the exponent 3 over 2 is equal to 8. So you can play around on your calculator and determine that. And if I'm working with log base 8, 8 to the exponent 1 would be equal to 8. You see that my y values are being reduced, and I'm dealing with a vertical stretch. How do you describe the stretch factor? So we see how those stretches are happening with those three graphs that were prepared for us. How would the graph of y equals log base 2 be related to the graph of y base log 64? Well, you need to think about the fact that 2 to the 5th is equal to 64, not 65. So we're going to get a vertical stretch by a factor of the reciprocal of that power. So 1/5. Whoops, my 5 should have been a 6. Monday morning is fun. 2 to the 6 equals 64. So it's a vertical stretch of 1 over 6. That's what we have to worry about there. And the policeman gives us that information. The transformation which maps y equals log base b of x to y equals log base b to the exponent n is a vertical stretch about the x-axis by a factor of 1 over n because of the relationship between the logs. So solved a similar statement, but trying out my rule of being able to move that exponent around. So if log base 5 of x equals 6, can I predict the value of log base 125? So I replaced 125 with 5 to the 3, and the converting between bases allows that 3 to come out as a fractional exponent. So 1/3 of log base 5 of x is equal to y, but I knew what log base 5 of x was. That was 6. So 1/3 of 6 is equal to 2. I could solve that in another form. And that's by saying, hey, 5 to the 6 is equal to x, but 125 to the y is also equal to x. 125 can be replaced by a power of 3, by power of 5, 5 to the exponent 3, and then set my bases equal to each other, set my powers equal to each other with bases that are the same. That means the exponents must be the same, and I was able to solve for y. We've got some transformations to take a look at. Let's shift down. So we're back to our ABHK information. So when I have y equals 2 log x, I'm looking at a vertical stretch in relation to y by a factor of 2. Here in the next one, I've got my h value being introduced, and like before, it moves opposite. So the graph is going to shift in which direction? So that's a horizontal translation 2 units to the right. And I've got a k value, which I can read directly off. That's going to shift the graph 2 units up. Vertical translation. Pardon me, 2 units down. Read it directly off. So something to check out today as we wrap up logs. These statements are supposed to be equal. Y equals log x to the 3 is supposed to be equal to y equals 3 log x using our rules for logs. But the graphs are different. The graphs are actually different for some of these relationships. Try graphing y equals log x cubed, y equals 3 log x. Compare that to y equals log x to the 4 and y equals 4 log x. What's actually happening there? And think of a reason why that might occur. You can check your answer book. We can talk about it a little bit later. So I want to see if you can come up with a conclusion for those graphs, some of them being the same and some of them being different. Think about the relationship of domain and range to the exponents that are being used. And now we're off to our last assignment, trying to put some graphing into action. Have fun. Try and start your practice test. We'll take time for that tomorrow. And we're testing on Friday. Thank you.